first session of the seminar for the year. So we start the year with a talk from Seonwoo Kim, who's actually right now visiting us in France, which is why he's not completely in the middle of the night. And he's going to talk to us about the spectral gap for the symmetric exclusion process.
Okay, thank you very much for the kind introduction. Now, as the Clément said, I'm now in Lyon. And today I'm going to talk about the estimate that we recently got with Federico. I see Federico in the IMPA, right? And so this talk will be based on the two recent collaborations with Federico Sau. And let's start. So I recognize a little bit of a few people who will listen to this talk for a second time. I did the same talk last month in South Korea, but this time I'll try to be much more in details because I have a slightly longer time. And is the sound still okay? No howling?
Yes,
Yeah,
yes,
okay.
I think it's fine.
Yes,
Okay,
it's
perfect.
okay.
Yeah, perfect, thanks. Okay, so I'll start by defining the model. So we will fix the model called symmetric inclusion process. So first we start with any arbitrary connected finite graph G. So you can just during the talk we can just think of for simplicity a one-dimensional graph, but we can think of any graph like a lattices, like a complicated graph, etc. So we fix G with vertices 3, and then we assume that we are given a conductance structure such that conductance the positive value which is assigned to each edge, and then it is 0 if there is not an edge. And then we also assume that certain site weights are given to the system such that for each x in the vertex, we give a value of alpha sub x, and alpha sub x is always positive at every vertex. And then we're doing the particle system, so we think about a specific space of configurations called psi k, and it's just the collection of all functions or particle configurations which is possible in the given space G. For example, like this one. Okay, and then until the very last slide, which is just the discussion, today I'll just fix the conservative case such that the number of particles are always conserved in the system. So to make the ergodicity of the system, we can just fix a parameter k, which determines the number of particles in the system. So number of particles here would be k. And then to define the system, we have to define now the jump rates for the rate for each particle to jump to neighboring sites. So the rate is given as this value. So this value can decompose into two parts. So we have this red part and the blue part. So for the red part, this is cxy, the conductance, times eta x alpha y. And this is just exactly the diffusive random walk, because each eta x number of particles at site x just performs a Poisson clock type random walk to neighboring sites y, but multiplied by the site weight alpha y. So this is just the random walk part. And then the second part, which is written here, is so instead of alpha y, we also multiply by instead of alpha y, we multiply by eta y, such that for the jump from x to y, it is more likely if eta y is also big. So a jump is more likely to observe if there are many particles sitting in the destination. So this rate will explain some kind of attractivity or stickiness of the system. So we can call it the attractive part. So these two values are summed here. So we have some kind of competition between the diffusive part and the attractive part, such that this particle system is quite complicated to analyze. So far, so good. And please interrupt me anytime if you have any questions, please. And then, so it's just like I want to shortly compare this with two very well-known particle systems. So first is just the independent random walks. So here you just step simply the diffusive part, which is cx eta x eta y, alpha y, and you can see it as a perturbation of this independent random walks. And then the much more important thing here is the symmetric exclusion process, which is we call SEP. And for the for our model, we call it SIP. And then for SEP, as many of you will know, so the rate is given as this one. So instead of plus alpha y, we have a plus eta y, we have minus eta y. So instead of encouraging the particle to jump more to occupied site, we kind of like have a hardcore recursion, such that in this step we can allow like only up to one particle at each site and etc. So like of course SIP and SEP are very very different in the dynamical point of view, but in some sense, like in a few algebraic aspects, they are quite also similar, and they also kind of share some duality properties, such that we can expect at least some kind of thing that can be similar in these two models. And as you know, exclusion process is much more well known to the community, and as I know, the reason why we call this model inclusion is because of the similarity and the change of sign compared to the exclusion process. Okay, and then the easy thing that we can realize here is that it admits a explicit stationary distribution, which we in this talk write by mu sub alpha k. And you can easily verify, actually, we have a detailed balance condition such that the process is reversible, and that the stationary profile mu k is a product type negative binomial distribution on the number of particles. Yes. And then now I will introduce the spectral gap. I'm sure that like most of you will very familiar with the spectral gap, but just to fix the notation and ideas, I'll be quite quick on this slide. So you can imagine the infinitesimal generator on the L2 space actually, but today we are dealing with the finite space, but no worries. So we write by L sub b alpha k as the generator, which is just the summation of all jump rates multiplied by the difference of the observable f. And then like it's very easy to see that this so for simplicity to keep positivity, we'll keep a minus in front of the generator, and that this minus generator is always a non-negative definite. This is because for any f, if you compute this inner product f and minus lf, then this is always non-negative, and which is exactly the actually the judicial form of this function f. I'll come back to this in maybe 20 minutes in the proof. And then like we also know that minus L is so because of the detailed balance, the minus generator is always self-adjoint. And then because the process is irreducible, we know that the dimension of the kernel of L is always 1. So just combining these three easy properties, we can see that we can just numerate the eigenvalues of the minus generator, which has exactly 1, 0, one simple 0 because of the constant function is always go to 0. And then all the other eigenvalues will remain positive away from 0. And then we just define the spectral gap to be the first eigenvalue, which is not 0. And then, like this spectral gap is very, very important in the many aspects of in the mathematical community, also in our community in probability. And the most important thing would be this following very simple lemma, such that the spectral gap is always the biggest or the optimal exponential rate, such that we can observe the rate of convergence to equilibrium. So if you choose any observable f here, and if you analyze this observable at time t, and if you compare this with the stationary observable in some L2 sense, and then you can see that this is always the case in some constant time exponential of minus lambda t. So this optimal lambda is always the spectral gap t. Spectral gap g. So like this kind of result is always you can find it on many particle system papers, like for example, hydrodynamic limits, like mixing time estimates, of course, like many metastability results, etc. Okay. And then I'll now introduce the conjecture of David Aldous, who recently retired in Berkeley. So this is the one particle spectral gap identity. So I'll briefly mention why the one particle case is quite important here. So you can just simply substitute k equal 1 in the original generator. And because if k equal 1, there is no interaction between two particles, so most of the generator just cancels out, and we obtain this following quite simple. Oh, sorry. Yeah. It's this simple observation. So there's only diffusive random walk. So this is actually equivalent to the weighted random walk on our graph v dxy and alpha x. And then we just to fix notation, we define the spectral gap of the entire symmetric inclusion process as the infimum of all gap, but we just restricted to k to be larger than or equal to 2 because we can also include 1 and then state the difference, but we put this thing because the truly interesting system only occurs if k is bigger than or equal to 2 because as I mentioned, one particle is just the random walk. So just for the notation, gap C is the infimum of gap k for k larger than or equal to 2. And then the famous conjecture, which for now I'll write it in the C version. I'll explain the original version in a few seconds. The Aldous conjecture can be formulated as just simply that the gap of SIP, the whole for K, is exactly equal to the gap of the one particle system gap 1, which is also the gap of the random walk. And the thing that in some particle system, why we may expect this kind of equality is that like in some systems, it's like no matter like how many particles they exist in the system, you can somehow reason to believe that like the number of particles does not really affect the rate of convergence to equilibrium. So only the one particle, somehow equilibrating in the system should be the one which gives exactly the exponential rate of convergence to equilibrium. So in that sense, to say that this equality holds means that this rate of convergence to equilibrium is just guaranteed by the one particle diffusiveness. Yeah, and then like I'll just briefly give the list of models that people concerned. So like if you so the first example like sorry mm, I think the Apple Pencil is out. Just a moment. Yep. Let's see it.
Seonwoo, maybe you can carry on with your finger, or
Okay, yeah. I'll
if
try
that's
this
okay, of
maybe in
course.
the yeah. I'll try it in 5 minutes. Okay, nice. So for the first model, which is the independent random walks, we obviously have the so-called spectral gap identity because in the independent random walk, we can like regard the system as just independent k random walkers, of course, such that the eigenvalues are exactly the same as the spectral gap is exactly the same with the one particle system. And then the second model called interchange process, the thing I made in an italic letter, is exactly the original model that David Aldous gave the exact spectral gap conjecture. So this is just the random process in the space of permutations of n labeled particles. And I think, as I remember, David Aldous gave this conjecture by some communication with Percy Diaconis in the 90s. And then after some suboptimal results regarding geometry, in 2009, I think they gave the full proof of the most general case by Apoio, Liggett, and Richhammer. And then this interchange process can also imply the result for SEP, because SEP can be viewed as some kind of projected process of this interchange process. And after this, actually, the conjecture was quite perfectly solved in 2009 or 10. But afterwards, people tried to study if this kind of identity or non-identity, holds in many other related models. So, for example, recently, Justin Saleh proved this set with non-conservative case, and he proved this identity in recently. And then, for the specific binomial splitting process proved by Matteo and Federico. And also we can prove that this equality does not hold, like, which means that this gap somehow decays. So get k decays somehow if k goes to infinity. So for this zero range process, actually this is the process where rate is uniformly 1, such that the more particles we have like a slowing down of the particles. And then they prove something like gap k is a scale of 1/k². So no, so oops, sorry. Can I yeah. So today I'll talk about the results. So we have two regimes. So in log-concave regime, we proved that our model SIP satisfies this spectral gap one particle identity. This was our first paper published last year. And then in the other regime, which is called non-log-concave, we proved that we can construct like a very rigorous model counter example such that we do not have this equality. So this is based on the recent work.
Sorry, Seonwoo, a quick question. So I'm not familiar with the binomial splitting process, but do all the true models have in common some duality properties or not?
You mean the binomial splitting or other models?
I mean, so independent random walk, interchange, and non-conservative SEP, I guess all have some duality properties, no?
Yep.
And the symmetric inclusion process as well. I mean, I don't know what log-concave or non-log-concave means, but I guess you'll explain afterwards. And the zero-range process does not have those duality properties.
Yeah, for zero range, no.
So is the true or false depends somehow on duality properties or nothing to see here?
I don't think so. Just duality. So in my opinion, I'm not an expert in duality, but just very helps the calculations and the research. But I don't think that duality is like related to either true or false of the conjecture.
Okay.
So interrupt quickly. So I think that the conjecture is actually true for some class of zero range processes.
Yeah, you're right. So I was yeah, you're right.
Yeah. So
well, I mean, independent random walks technically are zero range processes.
Yeah, exactly. Yeah. So yeah.
But I mean, some ones with that. I mean, they are attractive, but don't have duality necessarily.
Right.
Okay.
You're right. Yeah. Yeah. Thanks for the good comment. Yep. Right. Okay. If there's no any more questions, I will move on. Maybe I can try this. So okay. Yep. Next. Okay, then I'll go to the first result. Actually, I'm going to give basically three blocks of results today, and then after introducing each result, I'll try to give some concrete idea and sketch of proofs. So we'll first start with the first one. So this is the exactly the Aldous conjecture part. So first, we have this quite concrete inequality. So for any given graph and side place and any number of particles k, we prove this two-sided inequality. So first, we prove that the gap k is always upper bounded by gap 1. And then if we add this additional some suboptimal term here, so this is the minimum between 1 and alpha min, and alpha min is just the minimum of all side mates. And then if you multiply this by gap 1, and we also have this lower bound. So this was our first theorem in the first paper. And then very naturally we can have an immediate corollary that if alpha minimum is lower bounded by 1, this is exactly the log-concave regime. I will return to in a few seconds. Then we will have exactly the identity that gap k is always gap 1 for any k, such that gap c is just the infimum of such k. So we can conclude that gap c is always gap 1, such that Aldous conjecture holds for SIPs with alpha min at least 1. And then the reason why we just call it log-concave, we do not really use this log-concaveness, so it's not a big deal. But because if you recall this stationary prop for UK, then each marginal viewed as a function of the number of particles is log-concave if and only if this parameter alpha x bigger than or equal to 1. So just the notation, you can just skip this. So anyway, we proved that we have the identity if alpha min is bounded by 1. And the simple SketchUp proof is as follows. So first we can define the natural annihilation operator. So this is the operator AK going from the function space of k-1 particles to k, such that if you take if you evaluate a at some configuration eta with k particles, we just so you can, it's more easy to see in this way. So if it's normalized by 1/k, then we just like pick each particle uniformly at random, and then we just remove the particle, and then we evaluate this remove the k-1 configuration for given the function g, and just make the average, and we
So-
just like sorry.
Sorry, so AK goes from k to k-1, no?
So in this notation, you should go from k-1 to k. But the reason why we call it annihilation is that you can think about the dual operator now from k to k-1, from measure to measure, and then in this sense, this is going from k to k-1. But in the space of functions, we should go the other way around.
Okay.
Yeah, but thanks. So for just we just fixed notation without normalizing by factor k. And then this annihilation operator is enjoys quite a good property. So first we can with some calculus we can prove that this is injective. And then the more important thing will be this intertwining relation. So if we intertwine the annihilation operator AK with the appropriate number generator of number of particles, then so the in distribution the two things are the same. So the first one is removing first one particle uniformly random, and then run the dynamics with k-1 particles. This is exactly has the same law as first run the dynamics with k particles, and then remove one particle uniformly random. So this is the intertwining relation. So these are quite crucial. And then actually we can also define the somehow counterpart, which is the creation operator. So this is now we go the other way around. So this is A dagger. And then this A dagger, it has a little bit more complicated form, but the form is not important. The important thing is that if you define creation operator this way, we have this following joint property. So if you evaluate the inner product of A, K, G, and F, then the with some positive constant at the front, this is exactly the same as evaluating G and A dagger F in the k-1 space. So this is very crucial. So owing to this adjoint property, we can now prove that we can decompose this whole L2 space, which is exactly psi k, into two parts in an orthogonal decomposition manner. So first part will be the image of functions came from k-1 space by AK. And then the remaining part will be the kernel, such that this A dagger vanishes. And then we can prove by this adjoint property that they are exactly orthogonal with respect to Myohake. Yeah. Using this, so first we can easily prove the upper bound. So upper bound is just proving that get k is bounded by get 1. So suppose that we have this kind of this is the eigenvalue eigenfunction just equality for k-1 space. So such that suppose that lambda is the eigenvalue and g is the eigenfunction in the k-1 space. So g is not 0. Then you can calculate this term, and then by intertwining we can change AK and LK such that AK goes out, and then this minus LG is exactly the eigenvalue equation. We can substitute the eigenvalue, and then we end up with this one, such that so for this function AKG, we also have an eigenvalue function equality. Oops. Yeah. And the injectivity has a role here. So because G was non-zero and AK is injected, AKG is also a non-zero appropriate function, such that so given any eigenvalue lambda in k-1 space, this is again the eigenvalue in the k space, right? So this means that all the eigenvalue in the k-1 space is always included in the eigenvalue of k space. So we can just very easily see that gap k should be upper bounded by gap k-1. Gap k is the infimum of larger space, so it should be smaller than k-1, and you can just recursively apply this inequality to conclude that get k is bounded by kappa. So this part is quite easy. And then the lower bound is slightly more complicated. So we start with this very famous variational representation. So every spectral gap is the infimum of all L2 functions, the ratio of a Dirichlet form, and the variation. So and actually we have to exclude the constant functions, but we just ignored it. And then now we can decompose this whole infimum into two parts, which is the image of elimination and kernel of creation. And this is possible because of this orthogonal decomposition. This we had image and the kernel. So this is possible. And then what we can do is that we just put this thing still. And then for the left one, this is exactly, so AK is injective, so it just really moves all the structure in the K-1 system to K, such that this is exactly the eigenvalue representation for the K-1 process, such that it exactly get K-1. So to prove that this get K is lower bounded by this term, we can just prove that this right term can be bounded by alpha min gap 1 for every K. Then we're done. So we're trying to do this, and so this is the first idea is to reduce the Dirichlet form of the K Dirichlet form into one random walk Dirichlet form. So this was partially similar to the idea by Elmon and Saleh a few years ago. So like I'll be quite so you can this Dirichlet form can be written as follows. So you sum all the configurations. We have eta here, and then the rate, and then you just sum all this L2. This is square summations. And then because we have a eta x term here, we can just add a restriction that eta x is at least 1. And then the crucial idea here is that we reduce the space first into K-1. And the substitution we make is that we define psi as a eta minus delta x. Sorry, I forgot a summation in xy, of course. And then we can rewrite everything in terms of psi k. And then here we use the inequality for so this is so by renormalization we have k, and then we have a summation in the psi. And then the gap of 1 g alpha plus psi, and the variation of alpha plus psi of f psi. So this because if you see so if you look at these kind of terms, you can see the you can define this by f sub psi of function delta x, and this is of course the same function, and then this is f psi of delta y. So we can regard this as a function on the one particle system case, and then we can apply the variation representation here, such that we have this kind of dimension reduction from k to 1. And then we use the same idea, getting back from psi to eta, and then some calculation. So this is nilpotent, blah, 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 and we obtain exactly the term here. Yeah. So this is just reducing the Dirichlet form from k to 1. Okay, so so we reduce the Dirichlet form here to here, such that we are left to prove that this remaining term is bounded by 1 minimum 1 alpha min and gap 1. And this is done in the remaining part. So we're just comparing the gap of g alpha plus psi, which is perturbed by the configuration psi, and then the original gap 1, which is g alpha. To compare these two gaps in the same space, we just apply the well-known minimax theorem. So we compare the Dirichlet form and compare the variance or L2 norm, and then we have the exact appropriate constant such that these two, if we multiply these two constants, we have the optimal, the desired bind. Yeah, this is just the remaining calculation. I will not go into details. Okay. So now we approved the main results, first main result. Okay, now we'll go to the second one, which is dealing with the order of magnitude for the gap of SIP. So remember this was the first main result. So this is the two-sided inequality in the identity. Inequality. And if alpha mean was bigger than or equal to 1, we are done. But like generally, I mean naturally, you can also think about the case where alpha mean is not or smaller than 1. In that case, this part becomes so. In that case, so this part remains here, and such that these inequalities are not sharp. And to look at the order of magnitude, so we look at the slightly more restricted regime, where I call this condensing regime. So you remember the site weights are given by alpha, so we substitute alpha by epsilon of alpha hat, and then we just fix alpha hat as a just constant scale site weight, and then we send this parameter epsilon to 0. So in principle, this means that alpha is appropriately going to 0, which means alpha is very small, such that alpha mean will be, of course, smaller than 1, actually going to 0. And then in this condensing regime, the way we do so if you can change this two-sided inequality as follows. So first, this was actually gap 1 of G alpha, and this becomes exactly the epsilon pops up because in the one particular case, it is actually linear in alpha. So I'll just try to write it. So this was for the one particular case, oops. Maybe I already lost it. Yes. So this was just alpha y and f delta y minus delta x. And everything is linear in alpha. So for the one case, just epsilon pops out. And then here we just take the alpha minimum, and you can see that there's a epsilon square in the left-hand side. So the two-sided inequality is actually both two lower and upper bounds gives the different order of magnitude as epsilon goes to 0, such that it is way far from being sharp, right? And then to see which one is the actual scale of this gap of SIP, we can refer to this following metastability results. So this is the description. So these people maybe more or less 5 to 10 years ago, they proved that if we accelerate this SIP by 1 over epsilon, and then if we send epsilon to 0, then as a result, as a limiting behavior, limiting Markov chain, we get exactly the random walk by parameter alpha hat. So this convergence is can be stated in different ways. So it can be the trace convergence or finite dimensional marginals, or etc. There are many ways, but this is not important today, so I'll skip. And then roughly, actually, the convergence of the process itself does not really give the immediately give the convergence of the gap because they are quite different objects. But anyway, we can just at least we can believe that the scale of the gap should be quite similar, right? So we can believe that this accelerated SIP, which can be written by this, but accelerated by epsilon, 1 over epsilon, is somehow at least at the same scale at the gap of the random walk. And then this moving epsilon to the right hand side, we have this kind of expectation, right? So which means that the gap should be somehow in the order 1 of epsilon as epsilon goes to 0, such that we expect the right hand side to be more accurate. And this is exactly the thing that we proved. So in our recent paper, a paper with Federico, we proved that we can also lower bound this gap by a one scale of epsilon, but with some some suboptimal constant depending on G and head alpha. So in conclusion, if we collect this lower bound and this upper bound, we can conclude that this gap SIP has exactly the order 1 scale in terms of its epsilon. Okay. So for this, I will now. So it's quite impossible to give all the details that I did in the first main result. So I'll just give a sketch of proof and some key ideas. So we are trying to prove we are trying to prove this lower bounds such that the gap K is all bounded by epsilon times some constant, which just depending on fixed structures. So we again recall this decomposition. And then by the same idea, we can just prove that this infimum term can be bounded by something C and epsilon. And then to do this, like we simply recall the complete graph case, which means that in this case, G is always the complete graph of vertex N, or I just call it number of V. And then like all the edges are connected between all the vertices. In that case, like we can somehow calculate all the explicitly the eigenvalues. Actually, in this case, the eigenvalues are, as I remember, L phi minus 1 for L from 1 to K. And then like we can also prove that for each F belonging, each F belonging to the kernel of the creation, we have this exact identity here. So we have an identity such that the Dirichlet form and the variance have the ratio of K times this term, which is approximately K squared. So it gives us enough room such that this infimum can be rewritten as the infimum of some same functions, but we have a Dirichlet form of graph here, and in the denominator we have a Dirichlet form of the complete graph, but we have some reinforcement in the numerator. Okay, so to conclude that this infimum is lower bounded by some epsilon, we can it is enough to show that the you can upper bound the Dirichlet form of the complete graphs by the Dirichlet form of the original graphs, but with help of these terms. So we have a room of 2 Ks and then room of 1 epsilon in the denominator. So this is the thing we should do. And this is just so the the Dirichlet form can be divided into each edge, and then we are fixing the graph, so this does not give any difficulty in the scale. So we just divide it into each edge, and we prove that each Dirichlet form on each edge is bounded by the same scale. So just like the key step is just proving the upper bound. So we have the upper bound this Dirichlet part, this square summation part in terms of the original Dirichlet form. So this is just the sum n here. And the key is so as follows. So so I'll just start with the idea such that we can follow the key. So we have to decompose the edge such that we can have an appropriate L2 estimate of this Dirichlet summation. So remember that the remaining goal was this one, as I write right here. And then so just for the very simple case, just assume that X and Y are actually connected in the original graph G. In that case, you can easily see that actually this Dirichlet summand is actually included in this original Dirichlet form, right? So we just for the upper bound, you can just use the simple upper bound, and we actually do not need help from K square over epsilon. So we're done. So case 1 is very simple. And from now on, we assume that case 1 does not hold such that CXY is 0, which means that we have a connected graph. So there's a path from X to Y, visiting this Xi, and the path should be at least 2, of course. And then the first, so second case in this subcase, if you assume that all the sites at the middle are already occupied by eta, so this is the conversion eta, and this is eta minus delta x plus delta y. And then if all the paths are already occupied by eta, we can just construct a path according to the original SIP from eta to eta minus delta x plus delta y. I will just call it by zeta. And then from eta to zeta, we can construct these paths where we just pick a particle at x, and we just move it from xi to xi plus 1 for each I. So this is all eta minus delta x plus delta x1, and then blah, blah, blah. This is the, yeah. And then the idea is just to apply the Cauchy-Schwarz inequality such that the original L2 difference between eta and zeta, the value f, can be just bounded by the difference evaluate each path. Will be delta x plus delta x I minus delta x plus delta x I minus. Yeah. And then there's a remaining remaining conductors in front of the L2 difference. So we such have to renormalize it such that to upper bound the nabla sphere F, we have something like a infimum of each I, the ratio of the conductance. So it will be something like at x dxy. No, not 6y. And then here the mu of, and then the rate from here to one step forward. And then now we have the renormalization, so we'll have the Dirichlet form here. So this basically the idea is to apply the Cauchy-Schreiber inequality and then properly renormalize the coefficients such that we have the exact bound. So for this case too, if we calculate this infimum, we have a it should be no, this should be the maximum, of course. And then calculating this maximum, we get a term of k squared. So in case 2, we have a bound with the help of k squared, but we are still very nice because we did not gain help from 1 over epsilon. And then like from now I will be quite not go into details. So for the third case, we can the other case is that if all the sides are empty in the middle, but the size of the stack is properly bounded, then we can just, so in this case, it is not okay to just move one particle from X to Y in just one-dimensional way, because in that case, we have a bound something like K square over epsilon square, which is not okay in our case, right? So we need exactly the one order of epsilon, so this is not enough. So we have to construct another path, which gives the exact scale. So this is just take the whole stack and just move all the stacks one by one to X1. And then you take this one and then move it all the stacks to X2, blah, blah, blah. And you arrive in the configuration where we have all the stacks, which is neighboring Y. And then we just flick one particle to come here. And then you just move back all the remaining stacks back to X. So this is much longer. But using this path, we can easily, no, not easily, but calculate that we have exactly the appropriate bound. And then the next case is case 4. This is the same case where in the middle the particles are empty, but the first starting stack is very heavy. But in this case, the one-dimensional thing is not enough, so we have to further decompose the whole space into very complicated two-dimensional picture, which is illustrated here. You can see the details in our paper, but I just skip the details here. So the point is that also in this first case, we can have the same bound here, which is k squared epsilon. And then the actual fifth case, which is the general xy, we can just decompose the whole path from x to y according to if the sides in the way are occupied or not. We're just decomposing each path into small passes such that we can apply each case 2, 3, or 4 independently. And that is the idea. So like I'll just summarize here that we can have the exact bound here. Okay, so this is just the brief key ideas for the second main result. So I do not have really my time, but let's move on to the third main result. So actually, this is one of the main theme that we are quite focusing on our second paper. So I'll just briefly recall the Aldous one-particle conjecture, which that for many part systems we have a identity that gap C is exactly equal to gap 1, and then so there is some more sophisticated conjecture, so called the two-particle identity or conjecture, such that for reasonably many particle systems, we can believe that the whole gap, the system, is the minimum of gap 1 and gap 2, and in words, this means that so to equilibrate a system, like given arbitrarily many number of particles, we just have to look at two points. So first, like the one independent particle moving around the system. Also, we of course needed to equilibrate the system. And then this is the factor where like two particles are interacting with each other. So this is the factor where this interaction somehow slow downs the convergence equilibrium. And then this conjecture says that only these two factors are enough to analyze the full convergence equilibrium. So this is the conjecture made by recently, as I know, by Pietro Caputo. And so we tried to prove this identity for our SIP, but at the end we did not really have were able to prove the identity, but we had some result regarding the regime where epsilon goes to 0. So I'll explain. So for any given number of particles k and graph G, and you remember that we decomposed the side weight alpha into parameter epsilon and fixed alpha hat, and then what we prove as follows. So gap k over gap 2. When epsilon goes to 0, is like asymptotically converges to 1, which means that they are quite in the same value. But on the other hand, you can see the constant 2 here, and on the other hand, if you change 2 into 1, there exists a certain not very not very complicated, just a very simple torus. In this case, we can construct G and het alpha such that in the limit, the ratio between gap 2 and gap 1 is strictly lower than 1. So using this second inequality, we can immediately achieve the following corollary. So we can construct a explicit graph and the site weight such that gap C is strictly lower than gap 1. So this is just because the limit is bounded away from 1, we can take a graph such that this ratio is strictly lower than 1, right? And then like if you substitute here, and then we immediately get the corollary.
And is the graph really weird? Is it straightforward, or what does the graph
No,
look
it's
like?
very straightforward. Graph is actually torus.
Okay.
Just yeah. For a big enough fan. I'll get to this. So for this, I think I have to skip most of them. So a few main ideas, I'll just mention the keywords. So first, we have to decompose the so we are dealing with the regime where epsilon is going to 0, right? So we decompose the generator here, which is the original one. We just first is accelerated by 1 over epsilon, and then you can see two terms here. So we decompose the flow part as A, and the fast part by B, such that the accelerated L is a summation of A and 1 over epsilon of B. And then we use some limit theorem. So this is very clear result, plus some model-dependent calculation done by us, such that we can prove that this accelerated dynamics converges as epsilon goes to 0 to this kind of specific dynamics. So this dynamics is so pi k is the projection of the dynamics B, and then time to infinity. It's just the projection of this long-time behavior of B. And so this means that like it's very intuitive. So if epsilon is very big, then the B will just dominate the system into its equilibrium every time, right? Every time A makes a jump, just B will just push it again to according to the probability density according to the mechanism of B, right? So this is like the theorem is actually makes this part rigorous. And this means that the gap, this gap is exactly the gap of the accelerated process. This will converge to the gap of this process, which we write by double K. So it remains to quantify this value, which is actually the most technical part, but I won't have any enough time, but I'll just skim it. So this dynamics given by pi k a k is exactly some coalescing type dynamics of parallel particles. So this whole square is the transition rate function of the dynamics of pi k a k, and this omega of sub km is exactly the space of configurations with m piles. And then this dynamics is somehow, so it moves the pile with a simple weighted random walk. But if they can, they have a chance to collide, then they just collide, and then they make a merge, and then they make a bigger pile. Such that this dynamics, if m is, so in this region where m is at least 2, then this is transient. So at some moment, the two piles will coalesce, and then they will become a merged pile, such that they cannot come back. So m cannot increase, such that this whole rate matrix can be decomposed into block upper diagonal matrices, such that to calculate the whole spectral gap of the system, it just suffices to calculate each eigenvalue of this top matrices. Okay, so this is the thing that I did. So we did. So this spectral gap of this B coalescing dynamics can be decomposed as the random gap of the random walk, and then the smallest like a transient eigenvalue of each component. And then like from there on, so we had many calculations. So we defined some restricted annihilation operator, prove that this lambda km is always the value of lambda mm, which is the case when k in m. And then for lambda kk, this is just the dynamics of k particles, and this is exactly the not exactly, but somehow close to coalescing random walk, such that so if you have k particles, it will be of course much faster than to converse equilibrium. Then we have only 2 particles, right? So there's a lower bound inequality that we can bound lambda kk as lambda 2. Such that combining all these things, we can conclude that the limit here is actually equal to gap 1 if k is 1, and if k is as long as k is bigger than or equal to 2, there is a minimum between gap 1 and this lambda 2. And then so now it's quite easy to construct a counterexample. So as Clement asked me, so for the counterexample, we can just it suffices to find a explicit graph such that there's a strict inequality here. And then this is exactly as I mentioned, you can take any n torus of size n and dimension d, and d should be actually bigger than or equal to 2. And then cxy is actually just the constant conductance for all neighboring edges. And why we have this here, as I remember, gap 1 has a scale of 1 over n squared. But this coalescing type lambda 2 has a scale of 1 over n squared log n if d is for 2, and 1 over n to the d if d is 3. Such that so this is the scale. So if you take n big enough, then automatically we'll have that this lambda 2 is smaller than gap 1. So we have a automatic counterexample for big n. Yes, so this is the SketchUp proof for the third and last main result. I'll just spend maybe 1 minute for the discussion. Sorry, I'm very not used to this like that. So first we can so in the paper in the second paper we also discussed the non-conservative version of SIP, which means that we can attach abstract number of reservoirs in the system. So the omega and theta is just the parameters which controls it, and then we can with some so this is by duality. And the similar block decomposing ideas, you can prove that for reversible case where the reservoir density is constantly a single real value, then we can prove that the gap, the one particle gap, and identity holds. So every spectral gap for this value is exactly the same as the spectral gap for one particle. And there are some comments about the non-reversible case where we have a non-constant reservoir densities. This case, we can still find the eigenvalues as in the reverse case, but characterizing all the eigenvalues are quite out of reach at this point. And then we have some ongoing project with some collaborators. So this is the open just one-dimensional system where we have 2 reservoirs but with different density, and we're trying to calculate in the long time limit the number of particles transporting from left to right. So this is currently ongoing. And then we can use this idea to calculate many related models. For example, the Brownian energy process, we already had the result because BEP is actually dual to SIP, so we have exactly the same result. And then the beta binomial by we are in specific geometries, and then these days we are starting to discuss the general KMP model and blah blah blah. Maybe we can apply our concrete ideas to many related models. Okay, so this is good time to stop. Thank you very much.
Thank you, Seonwoo. So there have been a couple of questions during the talk, but maybe there are more.
Okay, so I think I already make this question to you, but I'm gonna make it again. Maybe now you know the answer. What about the log-Sobolev inequality, right? It's so in principle, in what you call the log-concave case, you expect the log-Sobolev equality to hold, no?
Yeah, but actually, after your question 1 month ago, so I asked Federico sitting there. So he said he had some attempts, but so in this in the idea, in the log solver infinity, you have the bound which depends on k. So instead, it is not very useful in the big k case. So
And we mentioned something about non-reversible, no? The non-reversible case. So there is this fact about ASEP, no, which is very mysterious. No, that's just, it's sort of it's a very puzzling thing. No, so we expect that on the circle, no, all these non-reversible nonlinear systems mix faster than the symmetrical counterparts.
Yeah.
But for the moment, the only system for which this has been proved is for ASEP, and the proof really uses a lot the particularities of ASEP, in particular, mainly this stochastic integrability type of things. So I don't know if you think about these things and whether SIP maybe could be simpler or not that ASEP or.
Yep. Yeah, I should say we didn't yet. Yep. Maybe we can try this. Okay.
Okay. Other questions?
So I have one more question, okay? So if you allow me to. So
Please.
I think you mentioned that somewhere. Well, you mentioned Carles Carvalho's laws, no? So Pietro has a method, no, in this paper in Alea to compute the spectral gap of the to relate the spectral gap on n sides to the spectral gap on 3 sides. If I remember correctly, it was very important to have a very explicit knowledge of the spectral gap for well, it could be 2 or 3 sides. It depends a little bit on the dynamics. And it was very important that to be uniform in the number particle. So I don't know if that implies that you can actually extend the spectral gap inequality for more general models.
Yeah, actually, you're right. So as I know, like there is I mean, like for me, like I believe it was 2, but I'm not sure. But so like in principle, the main idea was to believe that at least like the whole k-particle system, just the equilibrium just depends on just few number of particles, like 1 or 2 or maybe 3. I don't mean like yeah. So that's the reason why we can believe that quite large system with this kind of like a negative binomial stationary distribution should enjoy that kind of equality. Yeah.
Okay.
Hubert, I see you have the mic. Did you have a question? Oh, no, you didn't have the mic. My bad. Okay. Any other question? So if not, thanks. Let us thank Seonwoo again. And Seonwoo, I'll see you tomorrow.
Okay. Thank you very much.
Thank you.
Thank you.
Bye, everyone.
Bye.